the next is our next presentation. The next presentation is from Chen Jianfei, and he's from the Department of Electrified and Computer Engineering, University of Maryland, College Park. His speaking topic is the Hierarchical, Cascaded, Multilevel Converter with Continuous Uniform SOC Management for Battery Storage System. Thank you.
Hello, everyone. This is Jianfei Chen. I come from Department of Electrical and Computer Engineering, University of Maryland. Today, I will show a presentation titled by Hierarchical Cascaded Multilevel Converter with Continuous Uniform SOC Management for Battery Storage Systems. So, at present, the battery energy storage systems are popular in some applications such as electric grid connection, transportation, electrification, and renewable energy generation, and some grid applications. But large-scale energy storage systems suffer some challenges when it is used in this kind of applications. So such as first, the capacity, so how big it is at the lifespan, so how long it will run. And of course, we need to consider the cost of it. And most of them could be one very technical challenge could be the cell balancing for the battery systems. So why we see the cell balancing is very important for battery storage system, because because in a large scale battery system, there are many battery cells in series or in parallel. So regarding the batteries in series, so if the batteries with different volumes or SOCs, so they will be easily, we cannot easily utilize the full battery energy of the cells. So that is why we need to focus on what is balancing for each cells. And another solution is how can we balance the battery cells? So one solution is the cascaded multilevel converter based on the battery management system. So basically, this kind of multilevel topologies, so we can easily realize a charge and a discharge for each cell, and we can realize what is balancing or SOC balancing for the battery cells. So in that case, we can easily realize increase the utilization of the whole battery energy storage system. So this paper, we will show one topology on the right figure. So you can see this is our three-phase battery systems. So in each phase, we totally have 16 batteries in series, and with 4 cells in series, cascaded in series, and with unfolded circuits. So you can see that in each phase there are 4 medium units. So each unit have 4 cells. And the left figure, it is the 1 medium unit. We can see it is the basic cell of this kind of topology. So you can see that there are 4 battery cells cascaded with half bridge circuits. And on the right side, it is unfolded. So because on the left side, it is DC-DC transfer. So we need to generate our AC voltage. So what we can do is cascaded with a unfolded circuit. So we can easily realize 60 Hertz gate connected with the grid. So let me to show some more details for this kind of basic cell. So for the left side, there are 4 half bridge cascaded. So we can easily find that essentially it is like very similar to the MMC converter. So as we know, MMC converter, when they normally use phase shift modulation, because if we use phase shift modulation, we can realize a very high equivalent output frequency at the output side. And we can also realize balancing control. We can easily implement in practical application, since there are the carboners of just the phase shift with the phase angle phi I equal to 360 degree divided by -1. And the right side figure, this is output voltage, so Vn, that means the multilevel output. So you can easily find that there are totally line output levels, because there are 4 levels, 4 modules cascaded together. So essentially that will be 2 multiplied by 4 and plus 1. So we can easily get the 9. So for this kind of topology, how can we realize the charging and discharge control for the SOC balancing? So this kind of basic idea comes from the power electronic topology side. So if we just talking about one small cell, so you can see that one small battery cell with a half bridge S1 cascaded by composed of S1 and S2. So if we define the upper switch S1, the duty cycle will be S upper X. So that means if it is turned on, so this value will be equal to 1. If S1 is turned off, so that will be going to 0. So we define the instantaneous part of this kind of battery cell. It will be easily to find that the power will be equal to S multiplied by the voltage. So this is the voltage and the current, the output current. And this is for the instantaneous part. So if we talk about the average power of this kind of module, so we can see that this is related, it will be related to the modulation, because it depends on how long it will be turned on, turned off. Essentially, it will be how long it will be turned on, right? So that means related to the duty cycle of the S1, and that means related to the modulation. So if we define the modulation equal to the S1. So this equation will be described by M multiplied by the E and multiplied by the ITC. And it depends on what is the value of the M. So if M smaller than 0.5, so the figure will be the figure A. And if M over 0.5 but less than 1, so it will be like B. But if M is over than 1, that will be C. And charging discharging balancing, so we gave a control diagram of the whole battery system on this figure. So we're talking about this is a 3-phase battery system. So this side we have developed the proposed what is SOC balancing method. So it is based on the previous slide. So we can find that if we define the output voltage Vx, and then we can easily find that the modulation index will be related to the V divided by this voltage, and also related to the SOC here. We define like this kind of module SOC is Ix. So the total SOC will be depends on how many modules you have. And charge in that case, so this is. So you will see that this is when S1 is turned on, so that will discharge. So in that case, when the bottom switch is turned on, so that will be charging, right? So in that case, here we minus SOC and minus SOC. So this is a simulation result. If we want to realize the discharging, we can find that we can realize some phase angle between the inverter, multilevel inverter, and the grid side. So the red curve, it is the inverter output voltage, and the darker curve, it is the grid voltage. So if we control the inverter output voltage, the phase angle is leading the grid voltage. So we can realize the discharging. That means the inverter discharge energy to the grid side. So on the contrary, So you will realize the inverter output voltage lagged by the grid side voltage, so we can realize charging. That means the grid charging the battery side, battery inverter. So this is to verify our idea. So we realize a 3 kilowatt, 33 level multi-level converter prototype. So in this figure, so this kind of prototype it is implemented based on the battery cell. The battery cell has the voltage rating 11.1 volts, and with totally with 25 watt for each one, or we can say the watt. So it is a lithium battery model. So this model it is very complex. There are totally 48 modules, and each phase will have 16 modules, battery modules. So how can we? There are many power switches. How can we realize the control? How can we control them and realize what is SOC balancing? So here we use 3 DSP from TI company. So each DSP with 28335. So each DSP control one phase leg. So totally we need 3. And this is the hardware implementation for the algorithm. So how can we? This is for the implementation of the modulation. So here we use phase shift module to improve the efficiency of the code. So right now, I realize I set the CPU timer is 26 microsecond, and you can see here the red curve shows the code excitation just take 14.8 microsecond. That is much smaller than the interruption period. So that could be acceptable. And then we can also realize the fundamental period could be the 16.64 milliseconds. So in that case, the fundamental frequency we can see as 60 Hertz. And this is finally the experiment result. You can find that each phase voltage is very sensitive. You can see this kind of topology without any filter, we can realize very prefer sensitive waveform. And this is the bottom figure. It is shows the zoomed in figures in one phase leg. So you can see that you count it, so you can easily find that there are totally 33 voltage levels. And this is the right figure. This is I'm taking one phase leg. So phase leg, one phase leg, there are totally 16 battery modules. You can see that take around 40 minutes later. So we can find that every battery can the SOC can realize balance. Conclusion. So this control paper, we show a hierarchical cascaded multilevel for some large scale battery energy systems. So what we have done is first we show a project show this kind of topology. So this topology is developed based on hybrid combination of both H bridge and half bridge converters. And we also use the phase shift modulation to realize the PWM signal generation. Essentially, it is based on double reference signal because we want to improve the total excitation efficiency. And finally, we build this kind of prototype with the to verify our proposed converters and the uniform SOC managing method. Thank you, everyone.
Oh, okay.